Our last topic for this section is tangent vectors and normal vectors, and there's a really neat application of both of these that we're going to discuss towards the end. So we have something called a unit tangent vector. And if you just kind of decompose the words that we're using here, tangent vector means that we're using r prime. Anytime we're talking about a unit vector, it means that the vector is only 1 unit long, and the way that we change a vector into a unit vector is we divide by its magnitude. So the unit tangent vector, which is capital T, and it's a function of time, so I've got a little t in parentheses. We can calculate this by calculating the magnitude. We calculate this by doing r prime of t, because we know r prime of t represents velocity, but it also represents a tangent vector. And then anytime we divide a vector by its magnitude, it changes it into a unit vector. So this is our unit tangent vector. If we have some crazy curve represented by a vector valued function, and we want the tangent vector at a particular point, it's going to give us a vector that is pointing in the same direction of motion at that exact point in time. So let's say this is t equals 3, then this would be capital T of 3 if we made sure it was only 1 unit long. One thing that this is very useful for is for decomposing an acceleration vector. So remember, position vector r of t, it's got magnitude and direction. When we calculate its derivative, which we call velocity, the derivative always represents how things are changing. So this is a measurement of how magnitude and direction are changing. But remember, the magnitude of velocity we also call speed. We could also call this measuring change in position and direction. We're measuring the change in r of t when we do r prime of t, which is speed and direction. That means r double prime of t, if we keep on this theme of change, r double prime represents acceleration, and it's telling us how r prime is changing. So it's telling us change in speed and direction. So really, acceleration can be broken down into 2 pieces. We can have a piece that's telling us how our speed is changing, and we can have a piece that tells us how our direction is changing. Now, speed is just a number. It's the magnitude of our velocity. But if we accelerate, that means that our speed is increasing or our speed is decreasing. So acceleration is measuring the change in speed. So if we look at some random vector in space and we pick a point, acceleration is going to point into our curve, slightly into our curve. And what we want to do is we want to change acceleration to actually have 2 pieces to it. So I'm just going to approximate that a of t looks like that, because farther along we're still kind of curving to the left a little bit. That means or curving up. That means that acceleration will point up. And we can split this into two pieces. We could split it into a tangent piece, which tells us how our speed is changing, and we can change it into a normal piece, which tells us how our direction is changing. So this would be our unit tangent vector, and we call this other vector, there's always a 90-degree corner between them, we call that our principal unit normal vector. And there is a way to just calculate the principal unit normal vector. We're only going to discuss this vector in terms of how we can use it with acceleration, so I actually have an easier way for us to do this rather than calculating that principal unit normal vector. The reason it's called the principal unit normal vector is because there's actually two vectors we could draw that are normal to this curve at that particular point. We can also point a curve down and to the right, and it would form a straight line with n of t. But the principal unit normal vector always points into the curve. It points in the direction of motion. So without even knowing what this graph looks like, we could find acceleration at a particular point, and we can decompose it into two pieces. We can figure out how much of acceleration is pointing in the tangent direction and how much of acceleration is pointing in the normal direction. And that will tell us how much of our acceleration is being used towards changing our speed and how much is being used towards changing our direction. So what we have here is like a projection. I want to project, if A of t is the diagonal, A of t really is a sum of two vectors. We can figure out t of t by projecting, or we could figure out the tangential component of acceleration by projecting A of t onto t of t. So our ultimate goal here is to take our acceleration vector and split it up into two pieces. Capital T of t is a unit vector. Well, acceleration is not necessarily a unit vector. But I know that the tangent vector is tangent to my curve. I just need to figure out how to scale it properly to use for my acceleration. And then we also need a scalar to adjust our principal unit normal vector. So A of t can be broken up into those two pieces. We're typically not concerned with the t of t and the n of t. We just want to know, since they're magnitude 1, all of the magnitude from those vectors will come from a sub t and a sub n. A sub t, like I said just a second ago, is called the tangential component of acceleration. And this measures how our speed is changing. A sub n is our normal component of acceleration. And it measures how our direction is changing. And if you remember back a long time ago when we talked about projections, we had something called scalar projection, which means I don't really need to know the direction of my projection. I just want to know how big the projection is. And that's exactly what A sub t is. So A sub t is the scalar projection of our acceleration onto our tangent vector. So the way that we calculated a scalar projection is the tangent vector here is going to be represented by r prime of t, which is also v of t. The way we find a scalar projection is we find the dot product of our two vectors, and then we divide by the magnitude of the vector that's in the direction we want to go in. So this is really just acceleration dotted with velocity, all divided by speed. Calculating a sub n is fairly easy, because if we have an acceleration and we want to split that into an a sub t and an a sub n, if you look at this, remember opposite sides of a rectangle are equal. So if this is my a sub n, it's the same as over here. So here's a sub t, here's a sub n, and then here is our acceleration vector. We can just use a Pythagorean theorem to figure out a sub n. It would be the magnitude of a squared minus a sub t squared. I think this concept is really neat because we can take an acceleration for a vector valued function. The curve, we have no idea what the curve looks like, but just by finding our tangential and normal components of acceleration and comparing them, we can decide if we're at a spot on our curve where we're just driving straight, or we're at a spot that's very curvy. Because remember, a sub t measures change in speed, a sub n measures change in the direction. So if a sub n is really large, that means at that point in time, our direction is changing a lot. And if direction is changing, that means we're in a curve. If a sub n is 0, that means our direction is not changing at all. That means we're traveling in a straight line. So let's try one of these. Let's find the tangential and normal components of acceleration for a particle traveling along the path r of t 2ti plus t squared plus 1j plus 3tk at t equals 2. We want tangential and normal components of acceleration. Well, the tangential component of acceleration is just a scalar projection of our acceleration onto our velocity vector, because the velocity vector is the tangent vector. So a sub t is acceleration dotted with velocity over magnitude of velocity. So we need to figure out velocity and acceleration, which are our first and second derivatives. So r prime of t is 2i plus 2tj plus 3k. Our double prime, which is our acceleration, is 0i plus 2j plus 0k. Since we do have a variable left in here, if you want to, you can go ahead and plug in your time, or you can plug it in afterwards. It's completely up to you. So A dotted with V, that's just R prime dotted with R double prime. We get 2 times 0, which is 0. 2t times 2, which is 4t. And then 3 times 0 is 0. So we get 4t. And we specifically want this at t equals 2. So we could plug in 2 right now and get A dot V is 4 times 2, which is 8. So the numerator is going to be 8. And then we need the magnitude of our velocity, which is 2 squared plus 2t squared plus 3 squared. There is still a t left in here, so we're going to have to use our t equals 2 to get our final answer. So if t is 2, that's really going to be a 4 in there. Squared is 16. This is the square root of 29. So a sub t is 8 over the square root of 29, or approximately 1.49. Now we have no idea if that 1.49 is a large number or a small number. We have to see what it compares to in the grand scheme over all of our acceleration. To calculate our normal component of acceleration, remember, we need the magnitude of our acceleration. We're just going to do the Pythagorean theorem. But the magnitude of acceleration is our first step. And once we have that, we could also compare just the tangential component and decide if that number is large or small. So our acceleration vector is our second derivative. So that's 0 squared plus 2 squared plus 0 squared, which is just 4. And the square root of 4 is 2. So total magnitude of acceleration, change in speed and change in direction, is 2. 1.49 of that is part of the tangential component of acceleration. So quite a bit of it is going just towards changing our speed. So there's not going to be much left to go towards changing our direction, which is in the a sub n. And a sub n is just the other leg of our triangle in the Pythagorean theorem. We've got to start with our hypotenuse squared, which is acceleration, and subtract a sub t squared. And I'm going to use the exact value, so I can get an exact value for a sub n. This is 4 minus 64 over 29. If we get common denominators and combine, we get the square root of 52 over 29. That would be our exact value for a sub n. Or we could also change it to a decimal. It's about 1.33, or about 1.34. So I don't have units on any of this, and don't worry about that. But the most important thing is magnitude of acceleration was 2. And when we split this up into how much is going towards changing our speed and how much is going towards changing our direction, they're fairly similar. So just as much acceleration is going towards changing our speed as changing our direction. So most likely at t equals 2, we are in a curve, because we have quite a bit of that magnitude of 2 going towards changing direction, but we're also either accelerating or decelerating, because quite a bit is also going towards our tangential component, which measures the change in speed. Now it's possible that you could work a problem where all of your acceleration is in your tangential component and you get 0 for your normal component. That means that you're just traveling on a straight line, because remember, a sub n tells us how our direction is changing. Or it could be vice versa. We could have a sub n equal to our acceleration, our magnitude of acceleration. We could have a sub t come back 0. That means our speed is not changing at all, and all of our acceleration is going towards changing our direction.